rare case this year of a foreign visitor. I invited to the center, so Sasha Alexandrov from Institute of Basic Science.
Yeah.
So, yes.
Okay, thank you. So, first of all, I would like to thank the organizers, Sasha and Andrei, for this opportunity. And I was suggested to talk about the cut and joint operators. And actually some operators, which I call cut and joint operators. And my talk, of course, is motivated by some geometric input. So this project is motivated by some problems from geometry and to some extent from theoretical physics. But in my talk, I will focus on the mathematical physics description of the objects. So I will work with matrix models, Virasoro constraints, integrable systems, and all that. So I will start with some geometric motivation, but then I will switch to the more mathematical physics side of the story. And of course, I will be unable to give you all necessary details, so please feel free to interrupt me with your questions and comments. So I will start with an example, which many people here know very well. That is the concentric-Fitton function. Okay, so the concentric-Fitton function is a generating function of certain intersection numbers on the moduli spaces. So we choose moduli spaces. I think this topic is very well known in this room, but let me just give you a very brief reminder. Simplification. Moduli space. N of compact Riemann. Surfaces of genus G with n mark points. So this is a singular complex orbifold and complex dimension. This 3G plus n. And let me mention from the very beginning, we have a stability condition. So 2G minus 2 plus n should be positive. So today I will consider several types of the sum of the indices G and M, and I always will assume that this stability condition is satisfied, and if it's not satisfied, the contribution just vanishes. There are no unstable contributions. And so we have curves, genus G, n mark points. And on these moduli spaces, we consider certain cohomology classes. So for each marking points, I consider the line bundle, Gm, and the fiber over a given point. point sigma Riemann surface Z1 Zn is a set of remarked points. So fiber given by a complex tangent space. Of sigma and psi Gn Q is a first-term class. So we have some homology classes, and we want to consider the intersection numbers, the integrals, and Gn of these classes. Psi1, K1, psi n, Kn. These guys are some rational numbers. And so this integral vanishes unless the stability condition is satisfied. So we always assume that 2g minus 2 plus n is positive. And we have dimension constraint. So the dimension of this modular space, that is 3g minus 3 plus n, should be equal to the degree of the form. The form is just the sum of this indices chi. Okay, so we have infinitely many rational numbers. We want to investigate them. So to investigate them, we just introduce the generating function. Tau kw. It's a Schwitt tau function in the following way: x, the sum of all g and m, stable, g minus 2 plus m positive. Put h bar to power 2g minus 2 plus m factorial. And here we take the integral mgn sum k, k1, kn, non-negative, so 1 k1, sum n kn, and the product of some formal variables, ck1, ckn.
Small t's are the same as big t's.
Right. Not exactly. So, yes. So,
And about power of h bar, is it 2g minus 2 plus n or just 2g minus 2?
no. So it should be 2g minus 2 plus n. So it's not the genus expansion; it's the topological expansion. It's you can relate two expansions just by rescaling of the t variables because there are exactly n of t variables. But for me today, it will be much more convenient to use this topological expansion. Okay, so this is some object, and it's first of all it's formal series in h bar, and the coefficients of its formal series are just polynomials in t. And what I want to say is that small t's and capital T's are related by a simple relation, namely t k is equal to k plus 1 double factorial t to k plus 1. So I will always assume that small t's and capital T's are related by this scaling. What is the reason to introduce these small t's? The reason is that these variables are natural from a point of view of the integral system. Namely, it's Gibbon's conjecture proven by Katsevich that this function, this formal series of t variables, is a solution of the integral system. Explicitly, statement, theorem, the generating function W, conceptual tau function, is a tau function of the KDV hierarchy. And so this statement comes from interpretation of this intersection theory in terms of two-dimensional gravity. So it's from a point of view of theoretical physics, this generating function is a partition function of topological two-dimensional gravity. Should I say a few words about the KDV hierarchy?
You need something from
maybe not. At least not. There are several equivalent descriptions of this function, and one of them, which I will meet at some point, is the so-called Katsevich matrix. So for any function of this small t variables, we consider the so-called Nivell parameterization. And we define it in the following way. So for any function of t, if we substitute tk with 1 over k trace lambda equal minus k for some matrix lambda, we can assume that it's diagonal. When instead of the infinite dimensional space of variables t, we will have some finite dimensional space of eigenvalues of this matrix lambda. And this is what is called the Nivell parameterization. And it appears that with this Nivell parameterization, the conceptually different tau function is equal to matrix integral phi 1 h bar trace 6 minus 5 lambda square over 2. And so this is some normalization factor. And here we integrate over, let's say, Hermitian matrices of size n by n. And we take the asymptotic expansion at the critical point phi 0 equal to lambda. Yeah, so it appears that if we take the asymptotic expansion of this cubic integral, we get exactly the intersection numbers on this space. Okay, so this is an alternative description of this partition function, and there is another description, again equivalent in terms of the reciprocal. It appears that this tau function is a solution of an infinite hierarchy of linear equations. And these guys, the operators, satisfy the commutation relation of a subalgebra of a Virasoro algebra. Let me write them explicitly. One half of the odd positive m t m d f d t n plus 2k. Okay, so we have this system of linear equations, and it appears that this system of linear equations has a unique solution up to normalization. So there is a unique function such that satisfies this equation, and such of 0 is 1. So we can solve these equations, and there are different ways to solve them. In particular, and solve them in the form of Chekhov invariant topological recursion on some spectral curve. And today I will give another solution in terms of what I call the cut and join operator.
I missed what you said about Chekhov and Tarantin, because what up to now you said was known to some people in the audience, while Chekhov and Tarantin were not yet born.
Exactly. Yeah, I just want, I don't want to describe this Chekhov invariant topological recursion. I just want to say that this recursion is some universal procedure which allows you to start from a spectral curve and some structure in the spectral curve to construct the partition function. And for this case, the Chekhov invariant topological recursion corresponds to a very simple setup. So that is, we have two functions. X is z squared over 2 and y equal to z. That is the spectral curve equation is x is correct. y square. So I will not describe this procedure, but I just want to mention that there is a way to construct this partition function starting from using this Chekhov-Linear topology. This is one of the basic examples of this recursion. But today I want to describe another solution, and this solution is to some extent maybe simpler. So in addition to the resolve constraints, we have the dimension constraint. A dimension constraint has simple form 3h d over d h bar. Such item is nothing but sum over k odd k ck d over dtk. And now I want to substitute this t over dtk by this part of the operator. So these operators annihilate the concentrated tau function, so I can express this d over dtk in terms of the rest of the operator. So what I get is an equation, very simple form.
Is this dimensional constraint a corollary of Virasoro constraints, or it is an independent condition?
I don't think it's a corollary. I think it's somehow independent. So this is a form of a constraint I wrote from the very beginning.
So do you mean that Virasoro constraints have solutions which other solutions which don't satisfy this dimensional constraint?
No. I mean,
then it is corollary.
Okay, so this not exactly. So these equations, this equation fix you the constant here. So in principle, you may have a solution f of h bar of this form. And this equation fixes this constant. It tells you that it's not an arbitrary function, it's just one. So it's almost the corollary of the resolve constraints, but not completely up to this constant. And so this equation is essentially the equation I wrote from the very beginning.
Because in the right hand side you have almost a node.
Yes.
And that's one is written in terms of another.
So what I want to do is to express these guys in terms of the resolve constraints. So what I get is the following equation: W concentrated, and I will write it explicitly. of and to extra term T1 over 6 plus T3 over 8. So this is just nothing but a combination of the various order constraints. So we have these two equations, the dimension constraint and the combination of the various order constraint, and we exclude this operator from this equation. And what we get is an equation that describes dynamics with respect to the h bar. So the equation you get is d over h bar
Where from this T3 arises? T1 cube is from T1 squared there, yeah? Yes.
So these guys
is-
arises
yeah,
from-
it's from this one. And T3
from this one.
from this one.
Yes. So you, So you, yes. So you. Yes. So this is the equation you get, and let me stress that this operator W does not depend on h bar. It depends only on this t variable. So it describes you the dynamics with respect to h bar, and you immediately can write a solution. So the solution is that tau constitution is e h bar w constitution acting on the trivial function. And so this is what I call the cut and join description or cut and join operator. So this operator describes the constitution of
But
function.
in h bar expansion, the leading power should be h to the minus 2.
No, because I have the expansion into
It's not
g
just expansion.
minus 2 plus n.
Ah.
And this is always positive.
Here it is important.
Yes, so here it's important. So it's a formal series in h bar. And it's an explicit formula for the tau function, and you can use it for recursion. So you can find the coefficients of the expansion of the tau function recursively using this formula.
Whether this operator is homogeneous
This operator is homogeneous.
with respect to which weights?
With respect to the weight degree of T it is okay. So it's an operator of if dw constitution is equal to 3. So yes, this operator is homogeneous. Oh, it should be homogeneous because the expansion of h bar gives you coefficients which are homogeneous.
Sorry, I don't see that. The first term in the sum has a homogeneous degree -3.
Right. So it should be plus 3. Yes, exactly. Thank you. Yes, it should be minus 3. Yes, it should be homogeneous.
And there is plus.
Here is plus, here is minus. Thank you.
Надо не сначала, с конца смотреть.
Thank you. And so we have this expression, and we can find the coefficients of the expansion of the constitution tau function recursively. Okay. Logical expansion. expand tau such from the Fourier series H bar over power k. K starting from 0 to infinity. When these guys are given by recursion. Tau k is equal to 1 over k is operator W. Such acting on tau k minus 1. And all these coefficients are polynomials. So we have some polynomial, we have a differential operator. It's in principle it has infinitely many terms, but because of this degree constraint on each step of this recursion, only a finite number of terms of this differential operator contribute. So we have a polynomial recursion in terms of some differential operator, and this recursion is linear. So the coefficients of the non-connected coefficients of the tau function we can recursively obtained through this action of this operator.
Does it have some meaning in terms of initial integrals?
Yes. So these coefficients are some combinations of intersection numbers. They're non-connected intersection numbers in the Monte spaces. So these guys are polynomials.
As I understand, it's not very natural from the point of view of an integral because it mixes the contributions of different genera. Yeah? So if you consider matrix integrals the sum of the diagrams, like one of the authors of topological recursion claims, then, for example, here the first non-trivial term is T1Q plus T3. Yeah?
Yes.
The first is contribution of sphere
Yes.
of planar diagram, and second of a toric one.
Yeah, so somehow it's a recursion in terms of error characteristic of a Riemann surface with punctures. So G minus 2 plus n is a negative error characteristic of a Riemann surface. And so we have a recursion in topology of Riemann surface with punctures. Okay, so this is the kind of main example of what I'm going to describe today. So the observation is simple. So we have a description of a partition function in terms of one operator, which is cubic, which does not depend on h bar. And the observation is that such a description exists for a huge class of models. And I will try to.
So what is model independent? That it is cubic?
The model independent is that it is cubic and that the coefficients do not depend on h bar. So for huge class of models, there are cubic operators which describe the partition functions by this equation. And let me mention that it's not clear how this operator is related to some other properties of the Minkowski-Witten tau function. For example, it's not obvious that this equation, the solution is a tau function of the KdV hierarchy, and I don't understand how to relate this equation, this description, to the matrix integral. So probably there should be a way to relate the operator to the matrix integral description, but I don't know how to get it.
Sorry, that's your point. So you derive it from this homogeneity property in the Rassor constraint, yeah? So that the fact that matrix integral satisfies the Rassor constraint is obvious.
Yes.
Yeah. So you said that solution is unique up to a function which is fixed by this.
Yes.
So in a sense, you wrote, well, here or there, yeah.
Yeah, but
I cannot substitute here matrix integral directly, but in that way it's obvious.
Well, I don't know how to exclude the Virasoro constraints from this logic. So I need the Virasoro constraints. What I would like to have is the identification of this operator description with the matrix interval. I'm meeting the intermediate step. And this is what I
May I also ask a question? If you take the case Rossor equation multiplied by tk and sum up, then you have obtained similar cubic equation. Is it the same?
so what again? What?
Just take a Rossor equation number k,
Yes.
multiply by tk
Yes.
and sum up.
Yes.
Is it just the same equation?
More or less, yes. It's almost the same. So you have consider a combination of Rossor constraints, and you add the dimension constraint, which describes your derivative with respect to h bar in terms of derivative with respect to tk, and that's it.
So this recursion is just the same recursion that people usually use applying Rossor constraints.
Well, in some, I mean, people, there are different equivalent description of a conserved tau function. You have the topological recursion, you have the correlation, explicit formulas for correlation functions, Akonkov's formula, Sasha's formulas, some other formulas. So, of course, all of them are equivalent to the Rossor constraints because there is a unique solution. So.
Well, and another question: this W hat, is it from J infinity?
No, it's not from the J infinity. This is what I said. So I don't know how to relate this description to the integrable properties of the tau function.
So you see that it's not from GL infinity, what it means exactly, it cannot be written as some fermionic bilinear?
Yes, it cannot be written as some
It's not, W is not a symmetry of KDB
yes.
hierarchy, KP hierarchy.
Yeah, it's not symmetry of KP hierarchy.
Немножко поправить при помощи
with numbers. And there, the corresponding operator has a beautiful basis that can be described in terms of functions. Yes, can you find the basis in the space of polynomials in which this operator acts in a nice way?
Kind of, yeah. So. No, I'm not sure. I'm not sure. So.
Here there is common expectation, so Yosha says that it's very similar to zero mode of DeFi cube. If you
the zero mode, third mode, something like
third mode, whatever.
No, but
yeah, but something comes out of this consideration, and what exactly?
well, the coefficients here are.
Coefficients are different. They are
Yes.
from coefficients.
Yes.
But
Yeah, the structure is.
I think that one half can be fixed just by like this.
Well, you have three coefficients and you can fix two of them, but
Not all.
one of them is wrong.
Чуть-чуть выпадает.
Так, почти.
Okay, so let me show you some other examples when we have similar description, and at the end I will try to give you a general statement about such properties. So my next example is the so-called Grisant-Sweepen tau function. And I will define it in terms of the matrix model. Design was written in this new optimization. Is given by some matrix integral. Again, we take the asymptotic expansion, have some normalization coefficient, different one, e minus 1 h bar, and let's square phi over 2 plus 1 over 2 phi minus h bar and bar. Again, this is a tau function of the KDV hierarchy. And there is a nice enumerative geometry interpretation. Namely, there are so-called Norbury classes. G minus these guys are related to some supersymmetric version of the image of the system. And again, we consider the same generating function with insertion of these theta classes. And a conjecture of Norbury, which was recently proven, tells us that the intersection theory of these theta classes of t is again a generating function. Sum of gn h bar to g minus plus m factorial and gn So we consider exactly the same generating function with insertion of a theta class. And again, this is the tau function of KDV, which is given by the asymptotic expansion of this matrix. So again, we have the Virasoro constraints. Which are all almost the same. GW, KLEG equal to 0, but now the index starts from 0. And the dimension constraint will similar for h bar and the h bar of GW equal to some So again, we solve these constraints in the same form, and we get the same equation, an equation of the same form. Where this operator is somehow simpler than operator explicitly. So this operator is again homogeneous, and its weight is equal to 1. And again, we have same type of a structure. And now, what I want to say is again this operator is.
Before you have written that there was some odd letters, now it also.
Sorry?
Below you have written that K and M below does some C odd.
Yes, they are odd.
Below.
Odd positive.
This
So this is tau function.
KDV.
Yeah, and it's odd. It's always here. It's always odd. It's KDV, so we have dependence only on the odd time variables.
And if I take your matrix integral, this is horizontal cross written, and instead of 1 over x, there put x squared. 1 over 5 put 5 squared, yeah. What happens?
What? And you do not change our circles.
Do not change
Ah,
all
that's right.
the rest, yeah.
I don't know. I believe it will not be KDV anymore, most probably. Maybe KP.
It will be some, yeah, I think more this double chain. Okay.
Okay, so again we have some operator, and this operator again does not belong to the GL infinity algebra of symmetries of KP hierarchy, but it's related to the symmetries of the BKP hierarchy. So if
But wait a minute, if you sum up over all integers, not all positive integers, not necessarily odd, then it will be in GL infinity. And the contribution of even summands is trivial, so it's...
not exactly, because you have this coefficient 1.
No, both summands.
Each sum.
Why even numbers to why trivial? You said
What do you mean?
even numbers are trivial. Why even contribution?
Could you please repeat the statement?
No, you're right. You take derivative K even and
Можно получить, что ты хотел? Чтобы по всем не положительным?
ну, если добавить другие слагаемые, то так, чтобы он не изменился, чтобы его действие на этот самый потенциал не изменилось, а сам он стал все-таки уже бесконечностью. Ну, не получается действительно. Если К четное, М нечетное, то нам производное по нечетному времени мы умножаем на что-то ненулевое.
Это же какой-то они периодически стоят, поэтому нет никаких четких.
Ну да.
But
Рамонская, да. Рамонская.
so it's not clear how to relate it to the symmetries of the KP hierarchy, but it can be related to the symmetries of the so-called VKP hierarchy. So if we take tau is GW of T over 2, so if we rescale with T variables, if we divide the T variables by 2, then this operator W Alexandrov's is belongs to the symmetry algebra of the so-called BKP hierarchy. So from this representation, from this representation, it immediately follows that this is a tau function of a BKP hierarchy.
But didn't you say before that it's tau function of KGV?
Yes.
How can it be simultaneous?
Because all tau functions of KdV are solutions of BKP.
So it's not nothing new.
It's nothing new, but we can see it from this operator description immediately. So if we have this equation, we immediately know that the solution is the tau function of the BKP.
But why didn't you say before this about Kontsevich-Witten?
Because it's not true.
So not all tau functions of KdV are tau functions of BKP.
No, all tau functions of KdV are tau functions of BKP, but here we see it from the structure of the operator.
But Kontsevich tau function is also a tau function of BKP.
Right. But we don't see it
You
from...
don't see it from the cut-and-join equation.
Yes. Let me mention from the point of view of Chekhov and around topological recursion, this partition function is a generating function on the Bessel curve. Let us x is z squared over 2 and y is 1 over 2. Any questions?
Can you somehow comment because well you see that the form of the cut-and-join operator in one case says that it is a tau function of BKP, and in another case does not say that, though this is nevertheless correct.
Yes.
So then, what is the point? How do you see it? What is the property of this cut-and-join to say immediately that it's tau function of BKP?
Well, here the property is that if you rescale the T variables, it belongs to the symmetry algebra of BKP. In that case, it does not belong to the symmetry algebra. That's it. So it's just an observation, and I don't know if there is any deep structure.
And not isomorphic. I mean, in PKP case, we have different isomorphic structure of scalar product, and don't we have some? And we have some isomorphism between them. And then in Kontsevich-Witten case, we don't have some isomorphism to one of this.
What I want to say is very simple. So we have two operators, and we can ask ourselves, do this operator belong to some algebra, the symmetry algebra of the BKP hierarchy? So for the Resenko-Witten model, this operator is from the symmetry algebra. For the Kontsevich-Witten tau function, the operator is not from this algebra. Well, we can check it explicitly because we know how to generate cubic operators for cubic operators which give the symmetries of the BKP. Okay, let me give you another example. Or to be more precise, a generalization of the examples I just described, the so-called higher letter song. Words. On the physics side, we are related to so-called JT gravity. Again, we consider certain intersection numbers on the modular spaces, but now we add so-called kappa classes. Kappa k is equal to p star psi n plus 1. K plus 1. Plus 1. 2k homology classes. NGM. And 5 G plus 1 and Gn is the forgetful. And now we want to consider the intersection numbers of all possible combinations of kappa, psi, and theta classes. And we introduce two generated functions, tau alpha, for alpha equal to 0 and 1, alpha c and s. Again, x some gm, okay, g is positive, and bar g equals to xm. And we take some k, m, and some of the b, b1, bm, with theta grade, gn to power 1 max alpha. So for alpha equal to 1, we have no theta class, and for alpha equal to 0, we have this theta class. And we consider 1 kappa Vm, so 1 K1, Im Kn, and corresponding formal variables Tk1, and product of S, B, J, factorial over M. Yeah, and the result is sum of M. Okay, so now we have two infinite sets of variables. The T variables correspond to the insertion of psi classes, and S variables correspond to the insertion of the kappa classes.
There should be somewhere a sign of integral.
Yes, thank you. Exactly. So we have some integral G and okay, so we have this structure, and it appears that the insertion of the kappa classes is can be described just by the translation of the T variables. So we have the statement which we should use. Alpha Manizorov and normally 20. So tau alpha CFS is nothing but y tau alpha C 2k plus 1, so h bar q k minus alpha s over 2k plus 1 double factorial. And here I see tau alpha is equal to tau as written for alpha equal to 1, and tau Rosan was written alpha equal to 0. And these q polynomials are just some elementary Schur functions. Q j of s z. Where j is nothing but 1 minus e minus some s j z j. Okay, so the insertion of these kappa classes can be described in terms of a translation of the t variables by some polynomials of these new s variables.
This is somehow by Manfred's relations.
I'm not sure. Okay, and in this case, again, we can describe the partition functions explicitly in terms of some operators. Let me present you the description. We use formal series f alpha z, which is 2 plus 1 over 2 square root of minus 2y into gamma dt by t alpha plus 2 e z squared t over 2 minus some s j
In which sense is that theorem attributed to Manin-Zogrov and Norbury at the same time?
So it's so this is for alpha equal to 1 and this is alpha equal to 0.
But in any case, this theta class, it was already defined some years ago.
Yes.
And this
But
Because
you
for
did
alpha equals to 1, there's nothing.
Yes, for alpha equals to 1, there is.
For alpha, but theta class is very in the left side.
So we have theta class to the power of 1 minus alpha. So for alpha equal to
Just
1,
like definition,
it's just 1. Very little contribution of theta class.
Thanks. So that's the story about the expression of kappa classes. Why is the conservation written?
Well, it's
Manin-Zogrov, I mean.
what is the question?
So the result of Manin-Zogrov is adding up kappa classes and how to write it via the conservation.
Yes.
Значит, how to express monomial kappa
Kappa
class,
class
Yes.
is
forward of monomial написать class.
But that's basically the Manfred's law.
Is
Some basic equation doesn't have
that
all kinds of classes.
So we have some formal series given especially by this integral. This is the Huntley loop. And using this formal series, we introduce the coefficients. Rho alpha of k and n. It just take f alpha of z to the power k and take the coefficient in front of z to the power of 2.
You didn't say anything about gamma.
Gamma is the Huntley loop.
Where this f appears?
Where all this?
This f alpha is some function of z, yeah?
It's a function of z. It's a definition.
But so what is the relation to what was before?
There is no transparent relation. So this is how I define f of alpha. So I need these functions to define the cut-in geometry. So these are, so we have these s variables, and these s variables are these s variables coupling to the kappa classes.
And T is something different. That's
T is a variable of integration.
Yeah, because
Yes, it's just a formal variable. So we have these coefficients. We just take this formal series, take it to the power k, and take a coefficient in front of z to the power n. So these guys are some polynomials of S variable. And using these coefficients, we define the operators alpha k, sum m equal to k infinity, rho alpha of k m, j m, k ok. And here j, k are just the generators of the Heisenberg algebra. So d over dtk positive k, 0 for k equals to 0, and k, t, k for negative k. So these operators are just linear combinations of these guys.
So you go ahead and write it.
Sorry?
You have heads on both sides.
I have heads on both sides. Yes. So I just denote the operators acting on the space of t variables by head. Okay, so we have these operators, and the statement is that these generating functions for intersection numbers of kappa classes are just can be expressed in terms of with J operators exactly in the same way as for the Kontsevich-Witten and Rezangos-Witten tau functions. So we consider the operators U0 equal to k and z odd, G0 minus k, G0 minus m, G. 0k minus 1. That's 1 G minus k minus m minus 1. G m. G 0 minus 1 8. And similar expression for W1. I will not write it. Sum plus J minus 1 cube over 3 factorial. So we just substitute t and d over dt with these new J operators. J1 minus 3. And the theorem tells us that with all of these functions, these generating functions, again are given by h bar alpha acting on 1.
So alpha everywhere is like 0 or 1?
Yes, alpha is 0.
Principle, in those your formulas you can put any alpha, yeah?
Yeah, we don't have
values have no meaning.
Yes, at least the meaning is not clear. So yeah, here we always assume that alpha is runs from 0 to 1.
So with the cubic root?
Sorry?
With the cubic root for alpha equal to 1?
Yeah, it's a cubic root, but it's a formal series. So it's a cubic root, but this guy starts from the cube. So you just take.
Okay.
So it starts from z. And in this, let me mention that in the simplest case,
It's exactly what we use, exactly the same as we had before, right?
exactly the same. You just substitute.
Some plus coefficient is different. One over 8.
It should be exactly the same. You just substitute t over dk to jk alpha and ktk j minus k. Well, the idea is very transparent. So you have this this theorem, which I wrote, which describes the new generating function as a translation of the original generating function, and you can substitute this translation using the Virasoro constraints by the action of exponential of the Virasoro, by the action of some Virasoro group operator. And then you conjugate the original cut-and-joint operators with element of the Virasoro group operator. So it's equivalent to conjugation of all these variables.
But this one half, sorry, this one half in the second term, you can just take it out by just replacing J by some square root of J, right?
Yeah, this is what I said. So if you divide T by 2, then you get rid of this 1/2, and the coefficient will be equal. Well, you have T squared d dt and 1 2/2 T dt square. So if you divide
It's
T
like
by
square, 1 over square root of 2, something like this, right?
so you have a kind of T as 1. Right. Yes. So yes. If you want to get rid of this 1/2, you should divide probably by square root.
Then you can write all this as a like normal order set, right?
Yes.
And the only but you also have like a normal ordering constant, because in this sum you have something like z of -1, and this term is exactly this.
This one?
Yes, the zeta value term. Is it correct? So it's just what is written is just normal order of d phi cube first mode or minus not -1. Because you will have exactly so zeta of -1 is something 1 over 12. You have three possibilities because you.
Yes. So I'm not sure about the coefficient here, but maybe.
So what is the conclusion? That this is zero mode of d5
Нет, ну не zero mode, minus first mode. Минус первый мод, короче.
Нет, ничего, а все-таки где? До этого нам, значит, убеждаешь, что это не так.
Да, до этого была другая ситуация.
А что? Это же какая-то смесь того, что было до этого.
Там был еще J1 в клубе.
Ну, а почему так?
А потому что минус первый мод, а J1
Нет, я просто... Нет, здесь как бы там у нас был это периодический образование. Здесь обычный.
Нет, тоже код, тоже периодический.
А, здесь тоже код. Чем это все означает?
And if we consider the simplest case when we have only S1, which corresponds to the original Petersson volumes, and if we include only kappa 1, then this function is very simple. So we have alpha power to alpha plus 1 divided by 2 alpha plus 1 is just this explicit sum. From 0. And it's possible to express at least some of these coefficients explicitly. So these coefficients are given by some Bernoulli numbers, I guess. Okay, any questions?
It looks like in all your examples you derive this cut-and-joint from Virasoro. Other examples where you don't have Virasoro but have cut-and-joint?
No. So essentially it's a solution of the Virasoro constraints plus the dimension constraints.
So there is a spin case when Virasoro constraints do not determine the partition function. You have cut-and-joint in the spin.
Well, yes, you have an equation, but it's so for R spin case, you have, in addition to the Virasoro constraints, you have high W constraints. So for R spin case, the equation is less trivial, so you have equation of the h bar tau r equal to some w0 plus h bar tau 1 so on h 1 r minus 2 problem.
And who are these values? So first one is cubic again.
Yes.
And other.
High degree operators, which are constructed from the W constraints. And the solution is some ordered exponential. So it's d of h bar minus 1 But now, because these guys do not commute, you have to apply some permutation rules. Okay, maybe I will describe the last example, and we will finish with some general statement. Last example is given by the triple quotient inverse. So that and give sharing class horizontal. G of u sum from 0 to G and we will consider triple quotient integrals. With an additional column condition. So we have lambda of 1, lambda of 2, lambda of 3, such that lambda of 1 is 1 over to 0. And
So what is this condition? So your
lambda is some class, so it is a combination of lambda classes, and this is a polynomial of u. And
it has index g.
It has index of a g, so it's sum from g to 0 to g, and G.
And there you see what is this product.
This is just a class of homology. So we take three these guys with different
For which G?
parameters u for some given g. Yes. And so the point is that these integrals are closely related to so-called topological vertex, which describes the integrals of these classes are closely related to a topological vertex, which describes the topological string models on three-dimensional color manifolds. And here we have two independent parameters, so we will introduce u1 equal to minus p, u2 equal to minus q, so u3 should be equal to q over p plus p. And we again construct the generating function that alpha qp t capital take a summation gm h bar to g plus m factorial the same integral of mgm theta plus alpha gm and g of minus q g plus p and g q plus q and the psi classes. One, m, qm, product of tau k. So this is again the generating function which we construct using the same
Do you
rules.
mean exponent of this?
Here?
Exponent.
Exponent. No, it's not.
Yes, thank you.
It's correct.
Yes. And now the observation is if we apply certain change of variables, so let's change the variables. T 1 QP T1 and all five guys given by some linear change variables. Plus 2Q plus 1 square root of plus Q. Minus 1 plus minus 2 minus 1. Well, theorem, which is kind of tells us that if we take this generating function of q and p, t, apply with new change of variables, then this guy of t is the tau function of the KP curve. And for p equal to 0, when we have only one Hodge class, it's a result of simple theorem. And here is I believe, the maximal generalization of this KP integrability of the linear Hodge integrals. So the most general Hodge integrals which leads to the KP integrable generating function is this cubic Hodge integral satisfying the coefficient satisfying the Cavalier condition. And so again, we can construct the Virasoro constraints, we can solve them, we can construct with cut-adjoint operator. Probably I will not write explicit formulas. Again, it's cubic, again, it has the same structure. What I want to mention is that these partition functions are related to the matrix models. So if you consider so-called generalized Kontsevich model, or look at the same matrix. Kontsevich. From define E on H bar is V over phi minus phi into prime of lambda. Then these guys that better to say tau alpha, okay, tau 1 corresponds to case when the second derivative of v is a rational function z divided by 1 square root of p plus q z 1 plus q z square root of p plus q.
Some set of logarithms.
Yes, so this combination of logarithm and rational function.
Some formal expansion around some critical point.
Yes, again, you have to take a formal expansion for some critical point, but here, because the potential is not polynomial, it's a bit more subtle. First of all, you really need to take the size of the matrix to infinity, which you don't need to do for the polynomial Kontsevich models. And then you also have to, so if both P and Q are not trivial, then you have to supplement it by some non-trivial translation of the variables. So for general P and Q, the matrix model with this potential will give you the intersection, the generating function of the intersection numbers of triple Hodge integrals with some additional kappa classes.
Why this expression is not symmetric in P and Q?
It's not symmetric in P and Q
Because the original definition was symmetric.
yeah, but this change of variables is not symmetric. So to get the tau function, you need to apply this change of variables, and it's not symmetric. Okay, so let me finish with a general statement, which maybe I will not describe in any detail. So homological field theories and Chekhov on topological recursion. So I will not define any of these two structures which are closely related. So homological field theories were introduced by Kontsevich and Manin, and they were introduced to axiomize some universal properties of Gromov-Eaton theory. And so this homological field theory, or QFT, consists of a system of tensors. So we have some auxiliary space V complex space, n-dimensional complex space, and with a non-degenerate symmetric form, metric. Symmetric two-form eta. And we define consists of a system of tensors omega g and this. Omega g and this homology, again mgm times v star power m. And these tensors should satisfy certain conditions, which I probably will not describe. But for any homological field theory, we can introduce a partition function. So omega, again, exactly the same rules. M h bar to g plus m, m material, sum of k. Integral mgm omega g m a1 times e a m product j m psi j t j kg sum a and sum over. So now we have some classes, and to each element of the basis on this space V, we introduce corresponding infinite sets of variables. So again, it's some formal series of the T variables. And just to give you an example, the example is the Kontsevich-Eaton theory. So in this case, V is just C, and eta V1 is 1, and all omegas E1, when the omega is crystal concentric. For any, okay, so the statement is that there are different classes of cohomological theories. We will consider only the so-called semi-simple cohomological theories. And the semi-simple cohomological theories can be classified by the action of the given Telemann group. So the given Telemann group acts consequently on the space of cohomological, semi-simple cohomological theories. And it appears that all the partition functions of these cohomological theories can be described by some cubic cut-and-joint operators. So again, that J, A, K equal to D already T, A, K minus 1, positive K, and minus 1, T, A, K, negative K. Then for semi-simple this operator W omega, which is the sum I plus J plus K, I plus J plus K positive, some coefficients, A, J, K, A, B, C. Where these coefficients they depend on the choice of cohomological theory, but they are independent of the t variables and the h bar. So there exists such operator where the set omega is equal to e h bar w omega f. So all semi-simple cohomological theories can be described by some cubic operators.
All these coefficients are defined, they somehow related to the 3-point functions or
they are related, okay, so
to some structure constants or some algebra.
So as I said, this semi-simple cohomological theory can be described by the action of some group. And these coefficients can be related to this group elements, but in a non-trivial way.
I think some I plus J plus K should be 0, not greater. So
Sir?
it can be arbitrary number because before you had only degree minus 1 or minus 3, but now it's arbitrary number.
It's well, it's this sum.
Yes.
It's
No, I mean,
positive. It's not negative.
No, before you had this, the sum of three indices was either minus 1 or either minus 3, but now you're saying that the sum can be arbitrary number. So sometimes,
Yeah, so these operators are not homogeneous anymore.
these are not homogeneous.
So the leading terms of these operators are exactly the cut and joint operators for the conservative fitting or horizontal fitting, the leading terms. But in principle, there are infinitely many corrections.
So does it mean that K depends on some like scale parameter? I don't know.
So A depends on the choice of cohomological field theory. So if you consider something,
dimensional parameter, otherwise you cannot sum things with different dimensional. I mean,
well, it depends on what you want. So the action of this. So again, you can consider the recursion And on each step of recursion, you will have some polynomial and action of the differential operator on the polynomial. And on each step of recursion, you will have only a finite piece of this operator which acts on the trigger.
Finite piece.
Yeah, so in general, you have infinite sum here. But if you expand it in each bar, on each step of expansion, you only a finite number of terms in this infinite sum will give you a non-trivial contribution.
Нет, ну хорошо бы еще, чтобы размерность, поскольку у вас это в экспоненте стоит, хорошо, чтобы там размерность как бы была все-таки согласована. А она, вы говорите, что она согласована после разложения, а изначально нет. В физике считается, что должно быть изначально.
So this is the general statement from the point of view of chronological theories, and there is a similar statement for this Chekhov finite topological recursion. So if we consider spectral curve, again I will not give you definition, but so the Chekhov finite topological recursion allows you to reconstruct correlation functions or the partition function starting from the spectral curve. And here we consider the local spectral curve. So we consider local element surfaces. And the dx is a meromorphic differential. With finitely many simple critical points. And the local behavior in the critical point is given either by some area curve, as locally x is z squared over 2, and y is z plus some corrections, or the so-called basic curve. Again, x is equal to z squared over 2, and y is equal to 1 and z. So the local behavior in the critical points of x is given by one of these two possibilities. Then again we can construct the generating function z as of t, which is the generating functions of all correlation functions. And for this set of examples, again the generating function is given by the cubic cut and joint operator of this form. Okay, probably I should stop here. Thank you.
Спасибо. What about this general z omega? Is it tau function of anything?
Well, it's related to some integrable structures of associated with Frobenius manifolds, the Broglie-Jean structures. But in general, well, for me, in this talk, integrability means the KP integrability mostly. In general, this is not a tau function of KP or anything similar.
Should be some multi-component.
No, in general, it is not related to KP. At least it's not related to KP in any simple way.
I have just remark rather than question. So consider I speaking about topological recursion, consider the case when n equal to 1. So we have a meromorphic differential with a single zero. And assume that the curve is rational. Then it should have 3 poles. The number of poles for a differential is equal to 2, right? Or by the earlier characteristic. So there are several possibilities for the position of these poles. If all they are coinciding, so we have a multiple pole of order 3, this is exactly, we can put it to infinity, and this is exactly the KdV case on the left-hand side, the area function. There could be that this pole has one simple, there could be one simple pole of dx and one double pole. And this is the case of linear Cauchy integrals. And the more general case when all 3 poles are distinct. And this is exactly the case of these triple Cauchy integrals. And the position of the poles is governed by 2 parameters up to a scaling. And these are exactly the parameters of the, up to some change, parameters entering these triple Cauchy integrals. So all these functions that we discussed today correspond to topological recursion with dx having a global meromorphic function with a single zero.
То, что видишь, что дифференциальный функция студирует,
А если возьмешь с 2 нулями, то что?
А это с 2 нулями, это в тех же случаях это как раз двухматочная модель, которая тоже хорошо всем известна. И нет, согласно общему принципу, нет такой функции, для которой не существовал логический рекурс, если функция достаточно...
Нет определений, которые нельзя было бы описать матричной моделью.